questions from last time? Besides the obvious ones about paradoxes. Hey.
Oh, do you have an example of a self-consuming set?
No.
Is there even one? I should
Not that I know of.
C equals curly brace, C curly brace.
Yeah.
Like, that's terrible. Sorry. C equals curly brace 1 comma C curly brace. There you go. Self-inclusive.
C equals what?
C equals curly brace 1 comma C. I think you could just get rid of the 1 comma, but that would be a little boring, I think.
What do you
I don't know if that contains itself.
It doesn't?
This only contains two elements, 1 and C. Well,
C is the set,
1
so
and
it's
C.
recursively defining itself into the set.
Sure. Okay. Good. That works. That's a self-consuming set. But is that well defined? And I think that's where we get into trouble with naive set theory versus axiomatic. Because I don't think that's well defined if we try to somehow make it meaningful. Alright, here's my current attendance sheet. And I made this last night, so everybody on Canvas as of last night should be on there. So we were talking about sets and Venn diagrams, and then we branched off to talk about Russell's paradox. It's kind of a preview of coming fun. But let's go back to looking at sets and just some basic definitions. So we want the notion of a subset. So A is a subset of B. Remember what that means? If and only if. Every element of A, an element of B. And we write A is a subset of B like that.
Would you want to say that A is not equal to B?
It could be equal to, and every set is a subset of itself. Right? Because if I pick some set A, every element of this is also an element of this. So this is certainly true. But it's not a really interesting subset.
You wouldn't call it like a clone or a copy.
Similarly, the empty set is a subset of every set. Because every element in here is an element of here, because there are no elements in the empty set. But that's also not a very interesting subset. But these two things are always true. But we can modify this. If A is not equal to B, we can say A is a proper subset. And we can write that with a slightly modified symbol. Or we put a little slash through the horizontal line. Say it's a subset, but it's not exactly the same set. So it's an interesting subset. And we could make this look more precise. So A is a subset of B if and only if, remember the universal quantifier for all A and A is also also in B. It's just a more equation-like way of saying what we're saying over here. If I put a slash through that whole subset symbol, it means not a subset. So if A is not a subset of B, there must be some element in A that's not an element of B. Did everybody sign in? So A is not a subset of B if and only if there exists some element of A such that A is not an element of B. Does that make sense? So we have the universal quantifier, which means for all. We have an existential quantifier, which is a backwards E, which means there exists. So we could say A is a subset of B. A is not a subset of B. If and only if there exists an element A in A such that A is not in B. So that set on the left is a subset of the one on the right. This subset is not. And again, for any set, we know that these two things are always true. The empty set and the set itself are subsets. So every set has at least two subsets. So we can talk about something called the power set. And the power set of a set S is just the collection of all the subsets of S. So can the power set ever be empty? Why not?
Well, it would always include itself and the empty set.
It always includes S in the empty set. The power set always has at least two elements in it. And we can write a fancy PS to mean the power set. So if S is the set consisting of two integers, 1 and 2, what are the elements of the power set?
An empty set. Well, a set with one, a set with two, and then a set with one, two, so four elements.
Well, it's of course the empty set.
Yes.
But with the direct line.
So the empty set, the subset consisting of just this element, the subset consisting of just this element, and the subset consisting of both elements, which is the set itself. in general, there's nothing magic about 1 and 2. If this was an elephant and a zebra, the power set would still have 4 elements in it. Empty set, set of elephant, set of zebra, set of elephant and zebra. And so any set with 2 elements, the power set's going to have 4 elements in this case. So what about the set ABC? What's the power set of that contain?
Empty set of A.
Set of B, set of C, set of AB, set of AC. BC.
So it's got 1, 2, 3, 4, 5, 6, 7, 8 elements to it. And again, we can generalize a set of 3 elements of any particular nature. The power set will have 8 members. So is there a pattern here? Yeah. Do you have a question? Okay. Yeah, it looks like if we have n elements, we have 2 to the n elements in the power set. Is there a good reason for that?
Oh, true to the end, sorry, never mind.
Because if you consider them as like binary bits, you have 1 on, 1 off, so on and so forth.
Nice. So we could think of a subset as a binary number. If we have some set of elements, A, B, C, D, E, F, G, H. If we want a subset of this set, so here's our S. For any subset of S, we can ask 8 questions. Does the subset contain A? Does the subset contain B? Does the subset contain C? And so on. And each of those questions we can answer yes or no. And we can write a 1 if the answer is yes and a 0 if the answer is no. And so we can form an 8-bit number where this bit means, let's call this subset S1, is A contained in the subset? And 1 means yes, and 0 means no. And this position means, is B contained in the subset? And is C contained in the subset? And so on. And for any particular subset, we can write down a series of 8 bits that describe the subset. This is a subset that contains, if this is a 1, A, E, F, and H. And each subset corresponds to one of these 8-bit numbers, and each 8-bit number corresponds to one subset. And it's a 1-to-1 correspondence. So the number of possible subsets is exactly the same as the number of possible 8-bit integers that I can create, which from 250 we remember is 2 to the 8th, 256 numbers. So there's 256 subsets, and since the power set is the collection of all subsets, the number of elements in the power set is 256, 2 to the 8th. So that's kind of a hand-wavy way to see the conclusion. A lot of what you do in mathematics is you wave your hands, or you stare at clouds, or you drink excessively, and you get an idea, and then you take the rigor of mathematics and you try to prove it. Where the inspiration comes from is sort of irrelevant. The structure of the benzene ring came out of a dream the chemist had. He fell asleep and he dreamed of these carbon atoms holding arms, dancing in a circle. Doesn't matter where the inspiration comes from. But once you wake up, you try to use the rigor of your discipline to prove or confirm or experimentally validate your idea. And that's fun stuff. All right, let's continue talking about the size of a set. So we have a notation. And I'm going to modify this definition a little in a minute, but for a first definition, this symbol, putting two bars on either side of a set, is a way to represent the number of elements in that set. So, if S equals 1, 2, 3, then the size of S is just 3. Or if it's A, B, C, or X, Y, Z, or anything else. And so what we just did was we discovered that the number of elements in the power set of a set S is 2 raised to the number of elements in the set S. If S had 8 elements, this is 8. The size of the power set is 2 to the 8th, 256. And we're necessarily talking about distinct elements. Because if I say this set's the collection of the numbers 1, 2, 1, 1, 1, 2, 2, 1, 2, 1, right? We still want to say this is the number of distinct elements. So that would be a set with only 2 elements. But I'm kind of making an assumption when I say this. So what is the power set of the set of integers going to look like?
For all integers?
Yes.
It's going to be pretty dang big.
It's going to be pretty dang big. It's going to contain the empty set and the set of all integers. It's going to contain this set. It's going to contain the set of primes. Going to contain the set of multiples of 37. It's going to contain a lot of sets. And this formula isn't really going to make sense because the magnitude of S, the number of elements in S, is infinite. And the power set is also infinite. And we're saying infinity equals to the infinity, and we don't want to say things like that just yet. So I'm going to modify this and say if S is finite, meaning it has only a finite number of elements. So like the sets we've been talking about. We're going to extend this concept, though, on Friday, if things go according to plan, into a broader definition. And I'll tell you what we're going to define right now, but we won't get into it for another 2 days. We're going to be talking about something called cardinality. The cardinality of a finite set, S, is just the number of elements in that set. So the cardinality of the number of 200 level CS courses in this sequence is 4. 224, 22, 23, and 215. So for a finite set, we're going to use the word cardinality as a fancy word to say how big is the set, how many elements does it have. If S is infinite, cardinality is not going to be the number of elements, because that number is infinity. But cardinality of S will somehow relate to how big S is. In some way to be defined later. So for finite sets, cardinality tells you how big the set is, it just counts the number of elements. But if you have an infinite number of elements, cardinality will not be infinity. It will be something else that tells us in some way how big this set is. In particular, how big this set is compared to other sets that are also infinite. And this will be this notion we touched on yesterday that there's somehow more real numbers than there are integers. But there's just as many integers as there are prime numbers, as there are negative multiples of 10 million. Those sets all have the same cardinality. The reals have a bigger cardinality. There's more reals somehow. And we'll see exactly what we mean by that. And that'll lead us into some weird stuff on Friday.
Question?
Yeah.
So when we're talking about the first one, the number of distinct elements in S,
Mhm.
so does that mean if it's 1, 2, 2, then
That's just two.
that's just 2?
Yeah. All right, so that's a little teaser for Friday. And we'll talk about cardinality, we'll talk about something called the paradox of Hilbert's Grand Hotel, and we'll talk about something called the continuum hypothesis, which is another one of these undecidable questions that people used to hope they could make a lot of money by solving, but it turns out you can't solve it. This thing's running empty already, it's refillable. I don't know if they last. Can you see blue okay up here? All right, switch to blue. What's the power set of the empty set?
A set with an empty set.
It's the set containing all subsets of the empty set, which is just the empty set, and itself, which is the empty set. So it's just a set containing the empty set.
It's 2 to 0.
And this contains 0 elements. So the power set should contain 2 to the 0 elements. 2 to the 0 is 1. And this contains 1 element, the empty set.
So shouldn't you have 2 include brackets?
I could write it like this. But I'm using this as a symbol for that. Because you don't want to go too crazy with brackets yet.
Yet.
Yet. What's the power set of the power set of the empty set?
Power set of empty set and empty set, so 2 elements.
Right, is the power set of this thing that contains 1 element, which is the empty set. So all the subsets of this are the empty set, or this set itself. So it's got 2 elements. And the power set of that thing is going to have 4 elements. It's going to be the empty set. It's going to be this set itself. it's going to be a set just containing this element. And it's going to be a set just containing this element. Now we're getting into lots of brackets. This is probably really useful to someone. It's not to me. But it's a good exercise of working with the definition. This is one of these things where sometimes it's really, really helpful to have a good intuition for what's going on, and sometimes that intuition can do you a disservice. For me, at least. If I try to think about this too intuitively, I get tangled up in the curly braces. If I think of it as just find all the subsets of these four, a set containing these four elements, I can keep doing this until I get kicked out. All right, let's talk about ways to combine sets. If we have two sets A and B, we can talk about the Cartesian product of those two sets. And the Cartesian product is itself a set. And it's a set of ordered pairs. Okay, when we write things in curly brackets as a set, the order doesn't matter. But generally, when we write things in parentheses, like x comma y coordinates on a graph, the order matters. So this is going to be a collection of ordered pairs of things. It's going to be the set of all pairs A comma B, such that A is contained in A and B is contained in B. And it's all of those pairs. So for example, F is a set of foods. Fries, burger, chicken, salad. And D is a set of drinks. Water, soda. And we can ask what the Cartesian product of these two sets is. And it's a set of all pairs where the first element comes from F and the second element comes from D. So it's a set consisting of fries, comma, water, or the ordered pair of fries, soda, or the ordered pair of burger, comma, water, and so on. And we'll have 8 elements in that set. It's basically one element from here and one element from here. So you could think of this as all the ways that you could order an item of food and a drink. Now, is this the same as the product of D with F?
In the reverse or each of the pairs?
Yeah, it's a totally different set. Because this is the set of ordered pairs where the first element comes from our drink and the second element comes from our foods. And none of these elements are going to be in here, and vice versa. But if these two happen to have exactly the same set of elements, then the order is not going to matter. For example, x and y coordinates of points in a rectangle or in a square centered at the origin. And I mentioned that since I have 4 elements here and 2 elements here, their product set is going to have 4 times 2, 8 elements. And you can probably convince yourself of that intuitively, because for each of these n elements, we have m choices from here. And so we have n times m pairs. So this will be a useful way to put sets together. And it's Cartesian because this is how we do coordinates on the plane. All right, so set operations. And A and B are going to be sets throughout all of this. So this we call the union of A and B. And this is a set of all elements x such that x is in A or x is in B. So if I have the set 1, 3, 5 and I union it with the set 1, 2, 3, what do I get?
1, 1, 2, 3, 3, 5.
Technically I get that, but if we work from this definition, it should just be the set of elements that are in A or in B. And so I don't really want to write this. I'm going to say, well, it contains 1 because 1 is in A or B. It contains 2 because that's in A or B. It contains 3 because it's in A or B. It does not contain 4 because that's not in either set. It contains a 5 because that's in A or B. And it doesn't contain anything else because nothing else is in either A or B. So I would actually write it like that. But if you wrote it like this and you got rid of the duplicates and just listed distinct elements, you get exactly the same thing. So the union is putting things together. Take everything from here, just combine it into another set. The intersection, we write with an upside down U. And that's the set of all x, such that x is in A and x is also in B. So 1, 3, 5 intersected with 1, 2, 3. And which elements are in both of those sets?
1, 3, 1.
Just 1 and 3.
Is this related to be self-consuming?
No. Self-consuming was just a quirky thing to discuss a paradox. I mean, I shouldn't say no, but the reason I'm talking about it has nothing to do with that. Yeah?
Can you do these operations on more than 2 sets?
Yes, so we could do A union B union C.
Well, what about like intersection, where it's,
Same thing, it would have to be in all of those, in A and in B and in C.
how would you write it? Or is it just A, cat B,
Just like
and C?
this.
And that would be recognized as being in all 3 sets, not in either A or B, and,
It's the same thing.
Is there any order of operations for these things? Like you put unions and
It's commutative, it's associative. So if I were to do A intersect C intersect B, the only way I could be in here is if I'm in A and I'm in C. And to intersect with that, I also have to be in B. So because these ands are commutative and associative, the intersections are also.
but what if you say like A or B and C? Is that
There's no implied order, you have to use parentheses.
Oh, okay.
So if you want something like A intersect B union C, you gotta have parentheses to say what you want to do first.
If you don't, does it just go left or right?
I would say, which ones you want to do first?
No.
Rewrite your exam, dude. Yeah, I don't think there's, left or right's probably a good guess, but I won't do that.
Yeah.
Do you have a question or comment?
That was my question.
Okay, cool. So back to Venn diagrams. Here's the universal set. Here's A. Here's B. And this represents what? That's the intersection, because anything in here is in A and it's also in B.
Wouldn't you label that with the upside down U instead of a U? Because you got the square there, and in the top left corner you've got a U.
That's letter U for the universe,
Oh,
so that's different. That's the universal set. So this what is that? That's the union. So this is A union B. And this middle part, that's the intersection of B.
I don't remember what we call it, but there was something for union minus, they're saying.
Yeah, where it's coming up. But before we do that, let's ask a preliminary question. Now that I've erased all the definitions you need to answer this question. Is this always true?
Yes.
Yes. I mean, it looks like it from our picture. The intersection is contained in the union. What if you wanted to prove this? Someone offered you like $1 million, we could prove that this was true.
Outsource.
Outsource for like 10 bucks. Find some 215 students. What does it mean to say that something is a subset of something else?
All its elements are contained in the other one.
Yeah, every element in here has to be an element in here. So prove that if X is an element of the intersection, then X is an element of the union. If we can do that, by definition we've proven that the thing on the left is a subset of the thing on the right. But what does it mean to say that X is an element of A intersect B?
The elements, X such that X in A or X and A.
Right.
X.
And X and B.
Yeah.
So if X is an element of A intersect B, then X is an A and X is in B. That's the definition of being in the intersection. By definition of a union, if X is in A,
X might, wait. Right.
so what's the union of A and B mean?
X is in A or X is in B.
X is in A or X is in B. If X is in A, is X in A or in B?
Yes.
Yes. If X is in A, then X is in the union of A and B. So we just proved if X is in the intersection, then X is in the union. Therefore, the intersection is a subset of the union.
Didn't you also show this by mentioning that an intersection is X is in A and X is in B, and that a union is X is in A or X is in B. And then you draw a quick little truth table showing
Yes.
X and or logic, and you highlight the bottom row because that's 1 and 1.
And we're moving to that pretty quickly too.
Okay.
We're going to use something called a membership table, which will be a truth table for sets. Good. All right, let's see if we can get there before 10 of. So we know that this has got to be true. We're assuming everything's finite here, by the way. Since the intersection is a subset, it can't have more elements than a union. So let me show you a couple of examples. All right, A and B and their union. And what do you notice about the sizes of these sets, A, B, and the union?
Well,
It's the sum of the sizes.
Sure. The number of elements in here looks like the number of elements in here plus the number of elements in here.
Well,
the
it's
size
greater
of
than.
the union is bigger than the individual sizes of A, B, inclusive, and smaller than the size of the sum of those two things, inclusive. So, the size of A and B is less than or equal to the size of the union, is less than or equal to the size of the sum of those two, A
Cool.
and B.
Okay, I like that.
Because if you had an empty set, then if you added them together, they'd be the same size as the first one, right?
Right.
So. you
Okay,
actually include
cool.
that on one end.
Excellent intuition.
Would that include like if B, or if A was 1, 2, 3, 5, and B was 1, 2, 4, 6?
So suppose that,
Yes, because then it would be in the middle, yes, I think. It would be within the two bounds. Which is what I was trying to get at there. Well, that's actually gonna end up being the same size. I think you meant like, if there was,
If there was overlapping.
so we've got 4 elements here and 3 elements here, but the union is still only 6 elements. So over here, the size of the union was just the sum of the sizes of A and B. But over here, this has 4 elements, this has 3, that adds up to 7, but the union only has 6 elements.
Could you say it's just the sum of the distinct elements?
It's the sum of the distinct elements. The problem here is that we're counting 2 once here, and we're counting it again here. So if we just count individual elements, 1, 2, 3, 4, 5, 6, 7, we've counted 2 twice. So if we were to add the number of elements here and the number of elements here, but then subtract the number of elements that are not distinct, that should give us the number of elements here. So the size of A union B equals magnitude A plus B minus the number of non-distinct elements.
And the number of non-distinct elements here represented by A and B.
And the number of non-distinct elements is the number of elements in common between the 2 sets, which is the number of elements in the intersection. So we have a cool little formula here. Where did B and C come from? A, B. And this turns out to be always true for finite sets. Is the union of 2 finite sets always finite?
Yes.
If A is finite, it has a finite number of elements. If B is finite, it has a finite number of elements. The union is the elements in here plus the elements in here. That's going to be a finite collection of elements. So yes, the union of finite sets will be finite. What about the intersection of finite sets?
Yes.
Same thing, it's going to be smaller than the union. If A and B are infinite, is the union infinite?
Yes.
It's got to be, because A alone has an infinite number of elements, and everything that's in A is going to be in the union. If A and B are infinite, is the intersection infinite?
Not necessarily.
Not necessarily. Got an example?
If A was all odd numbers, B was all even numbers.
If A is all the odd numbers and B is all the even numbers, the intersection is the empty set, no elements. So the intersection of infinite sets can be finite or infinite. Something's not symmetric somewhere. All right, last thing I want to mention in the last 90 seconds, this notion of a universal set. So let me use a letter U to mean the universal set, and here's some set A. We can talk about the inverse or the complement of a set. And it means everything in the universe that's not in that set. It's all the other stuff. So if A is a set of even integers, the complement of A is a set of odd integers. If A is a set of prime numbers, the complement of A is a set of composite numbers. If A is numbers bigger than 10, the complement of A is the set of all numbers less than or equal to 10. But when we write a complement, there's always an assumption that we know what the universe is. If I just say, A is the set 1, 2, 3, and I ask you to tell me what the complement of A is, you don't have enough information to answer that. Am I talking about the space of integers, the space of real numbers, the space of numbers and letters and animals? So you have to know what the universe is to be able to complement this. So we'll talk about a slightly different form of complementing, which is negation, tomorrow. And then we'll start tying this into digital logic. And we'll do a bit of work with summations and sequences and matrices. And 10,000 other pages of things that I have here to go through in one